Under sequential circuits is the registers and counters. Storage elements, if we say storage elements, that is latches and flip-flops, are essential part of your sequential circuits. If a sequential circuit without this storage element, it reduces to a purely combinational circuit. A circuit with storage element alone is considered a sequential circuit. Circuits that include storage element are usually classified by the function they perform rather than by the name of sequential circuits. Most functions are as a register and as a counters. A register is a group of storage elements, each one of which is capable of storing one bit of information. An n-bit register consists of a group of n storage elements capable of storing n bits of binary information. Sometimes there are registers with combinational circuits or combinational gates. These gates perform certain data processing tasks. The storage element holds the binary information, whereas the gate determines how the information is transferred into the register. A counter is a special type of a register that goes through a predetermined sequence of binary state. The gates in the counter are connected in such a way as to produce the prescribed sequence of state. So we have this first type of our register, the parallel load registers. So we have your clock input that will trigger all the latches on the positive edge of each pulse. So most usually, registers are using D latches. So when a clock is at positive, the binary data available at the 4 inputs, which is connected to X, or we call that one as X, X0 up to X3, are transferred into the register. The 4 outputs, we have Q for D, or the rightmost D latch up to the first D latch in your left, is connected to your Y. So these 4 outputs can be sampled at any time to obtain the binary information stored in the register. The input clear is connected to a active high R. R is that means reset. When this input goes to 1, or we put our clear equals to 1, all the data in your latches or flip-flops are reset asynchronously. This means it will clear all the previous data in the latch. The input set is connected to the active high S. S is set. Then it used in setting the data inside your latch or flip-flops. Then we have another type of your parallel load register, this time with a control. So at load, if your load input is equals to 1, the data at the 4 external inputs, that is our X, are transferred into the register with the next positive edge of the clock. When your load is at 0, the outputs of your D latches are connected to the respective inputs. As you can see, your Q is connected to the first AND gate, when your load is 0, therefore the first AND gate is active, and this will be your input to your D. So why it is being connected back to your D? Because the, the D or the D latches does not have a no charge condition. Then we have a shift register. A shift register is capable of shifting the binary information held in each cells of each neighboring cell. So it will hold information and it can shift the information in each cell to its neighboring cell. So the logical configuration of your shift registers consists of a chain of storage element. So we have storage element connected in series or what you call in cascade with the one output of the one latch or storage element connected to the input of the next latch or storage element. The simplest shift register is one that uses only storage element or flip-flops or latches. And these are what you call your shift right register and shift left register. So for your shift right register, we have this circuit. We have your input at your left side and your output at your right side. We designated your latches as A, B, C, and D, and this is a 4-bit shift right register. So in this configuration, in order to store a 4-bit binary information into the register, we need 4 positive edge clock pulses. So the serial input will determine what goes into the leftmost latch during shifting, and the serial output is taken from the output of the rightmost latch. So if we have to consider that an information 1010 be stored into the register, first we have to clear the register by putting clear input to 1. So therefore, your register at latch A, B, C, and D have an initial value of 0. And our input in your latch A, where your input is connected at latch A, is equivalent to 1010. So the first positive cycle encountered in your register, your 0 in your input will go to A, then A to B, B to C, C to D. A second positive cycle or pulse encountered by your register, the input, that the value of your input with this one will go to A, then A to B, B to C, then C to D. The third positive pulse, your 0 in your input will go to A, the 1 in your A will go to B, B to C, C to D. And the fourth positive pulse, the last value in our input with this one will go now to A, then A to B, B to C, C to D. So if we have that data 1010 and we want to store that or to move that to your register, we need 4 positive pulses. Then one of the application of this shift right register is binary division. If we have to consider that your register, a 4-bit register, this type of register, we have A, B, C, and D, has an initial value of 100. So we have A, B, C, and D. In your register, initial value is 1000. Then we have to have an input which is equivalent to 0, which is being connected to your E LUTs or D LUTs with designation A. And the numerical value of your initial data inside your register is equivalent to 8. The first positive cycle that your register encounter, then your 0 will go to A, your 1 in your A will go to B, then B to C, then C to D. If we have to get the numerical value, what is stored in your register, it is now equivalent to 4. Second positive cycle, it will move your A to B, B to C, C to D, and input from outside going to your A. So the numerical value of your stored data inside your register is now equivalent to 2. And the third positive false, your last input data will go to A, then A to B, B to C, C to D. And the numerical value of your stored data in your register is equals now to 1. So we have a division by 2 to the n. Where your n is the number of pulses that your data is shifted to the right. Then we have shift left register. This time, our input is now at your right and your output is connected into your D latch designated A. So since it is a 4-bit register, if we have to store a 4-bit information into this register, we need 4 positive clock pulses. The serial input determines what goes into the rightmost of your register, and the serial output is taken from the leftmost of your register. So if we have to consider this information 1010, we have to store that one into the register. First, we have to clear the value inside your register by putting clear input to 1. So therefore, your register with lots A, B, C, and D has an initial value of 0. And we have your input, it is at your rightmost side of your register is equivalent to 1010. First positive false, your 1 will go to D. D will go to C, C will go to B, then B will go to A. Second positive cycle, your data input with a value of 0 will go to D. The D before this positive clock pulse occur, after a positive clock pulse occur will go to C, then C to B, then B to A. Third clock pulse, your 1 in your input will go to A, to D, then D to C, C to B, then B to A. And in the fourth clock pulse, your last data in your input side will go to D, D to C, C to B, and B to A. So it means if we have to store a 1010 into a 4-bit shift left register, we need 4 input pulses. Then, one of the application of this shift right register is binary multiplication. If you have to consider that the initial value inside your register is 0001 base 2. Since we have 4 latches in the register, so the initial value is equals to 0001. Then we put an input to your rightmost with 3 0. The numerical value of the data inside in your register is equals to 1. A positive clock pulse that your register encounter, it will become 0010, or your input 0 will goes to D, your D to C, C to B, and B to A. Then, if we have to get the numerical value what is inside in your register, it is now equivalent to 2. Another positive cycle, that is our second positive cycle, your second data input will go to D, D to C, C to B, B to A. And if we get the numerical value what is inside in your register after second positive cycle, it is equivalent to 4. Then third positive cycle, it is now equivalent to 1000, or the data in your input side will go to D, D to C, C to B, and B to A. The numerical value in your register at third positive cycle, it is now equivalent to 8. So therefore, the multiplication of this type of register is by 2 to the n, where n is the number of pulses that your register encountered in order for your 3 input to be stored in the register. Then we have the serial transfer, transferring information from one register to another. So we have register A and register B. Register A is our source register. We want to transfer the data in your register A to B. So register B is the destination register. So as you can observe that the output of your register A is being fed back to your input of your register A. This is to prevent the loss of information stored in the source register or register A. It is an information on register A is made to circulate by connecting a serial output to its serial input. Then another type of the combination of your shift register is that we can combine serial shift right and serial shift left using a 2x1 MUX. So we have your selector SO that will determine what shifting are going to perform. So if SO is equals to 0, the operation is shift right. So that is, we have your input at the leftmost part of your register. If SO is 0, this will enter to your register from rightmost. Then, if SO is equals to 1, the operation is shift left. So we have your input from your left or from your right going to your left. So that is serial input from your right side that is going to your left side. Then for our counters, it is a register that goes through a prescribed sequence of states upon the application of input pulses. So the input pulses may be a clock pulse or may be originate from some external source and may occur at a fixed interval of time or at random. The sequence of states may follow a binary number sequence or any other sequence of states. If a counter that follows the binary sequence is called a binary counter. So there are two categories of your counters. We have the ripple counters and the synchronous counters. So ripple counter is the same as your asynchronous counters. So for ripple counters, we have this one. So all of your G key inputs are connected to 1. So it means that your output Q will toggle every time that there is a positive clock pulse at your clock input, and that is only at your CP, where CP is connected to a clock, and your next G key, your CP is connected to the output Q, and so on. So if the output Q is equivalent to 1, so it will force your Q in the next flip-flop to toggle. So we have also clear input, which is connected to your reset. So at first, we have to make your clear equals to 1 so that we can initialize the value of your counters are all 0. So first clock pulse at your right side occur, then your first flip-flop in your right side, the output will toggle because we have a clock which is equals to 1 and G and key is connected to 1. So from 0, it will become 1. A second clock pulse occur, so your D flip-flop or D G key or G key designated as D will toggle. From 1, it will become 0. The output of your D before the clock occur is 1. So this one, during the time that your clock at your D is equivalent to 1, it will ripple or force your C flip-flop to toggle because the clock input of your C flip-flop is now equals to 1. So from 0, it will become 1. For your B, since your output of your C is 0, then there is no change of your B as well as for your A. On the third clock pulse, your D will toggle. From 0, it will become 1. Since the previous output of your D is 0, so there is no change in your C. The fourth clock pulse occur, so your D will toggle. From 1, it will become 0. So the previous output of your D is 1, and this is the input of your clock input of your C FF. So your C will toggle. From 1, it will become 0. And the output of your C before it toggles was 1. And that 1 is the input to your CP on your B. So therefore, B is now equivalent to 1 because it will toggle from 0 equals to 1. And that is the same as 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. On the 16th cycle, your D will toggle since D has an output of 1 before the 16 pulse occur. So therefore, C will toggle. Then this also will toggle your D and your E will also toggle, or that is a ripple effect. So your 16 now has a value of 0 for your E, B, C, and D. So it means that in the 16 pulse, your sequence will return to its initial value. So the maximum count of the 4-bit counter is 15. And it is equivalent to, or your count can be written as 2 to the n minus 1, where n is the number of flip-flops. And it is called binary up counter. For the binary down counter, we have to rewire your circuit that your output connection is at Q bar. So now we have your output at Q bar. So since it is Q bar, all the complemented value of your Q will be your output of this counter, and it is called binary down counter. A combination of up and down counter is by the use of your combinational circuits or AND or. So if your control up, so we have an up control, it is connected to your combinational circuits. If it is equivalent to 1, the operation is up because your active AND gate is connected to the positive output of your JK. And if up is 0, your Q bar is connected to the first AND gate, which is your inverter of your up is connected. So if it is 0, then the first AND gate will be active. So that is your down counter. Then we have also modulo counter. A modulo counter, it is a sequential logic circuit that follow predetermined sequence of counting states which are triggered by an external clock signal. So the number of states or counting sequence through which a particular counter advances before returning once again back to its original first state is called modulus or mode. In other words, modulus is the number of states that the counter counts and is the dividing number of the counter. So we have this modulo 10 counter, or another name of modulo 10 is BCD counter. So we have this circuit. So initial it is 0. First clock pulse equals to 1. Then therefore we have 1. Second it is 2. Third it is 3. 4 it is 4. Fifth it is 5. Sixth it is 6. 7. 7. Then 8. 9. Then 10. At 10, as you can see, it will go back to the initial value because your 10, we have your 1, this is 0, this is 1, and this is 0 when you are at your 10. Since this is connected to your AND gate and also to your AND gate, so we have a 1 here. And it is all connected to your reset input of your J key. So it will reset all your data back to its original value, which is your initial. So there are 10 pulses that your modulo counter can accept before it will reset to its initial value. Then we have a modulo 12 counter. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So 12, we have now a 1 here, 1, this is 0, and this is 0. So therefore, we have 1 and 1 in your AND gate. So we have a 1 which is connected to all your reset input of your J key. So it means that at 12, it will go back to your 0. Then we have modulo 6 counter. So we have 1, 2, 3, 4, 5. When it is 6, so 6 that is 0, 1, 1, 0. So your AND gate is connected at C and B. When C and B is equals to 1, so your output of your AND gate is connected to the reset input of all the J key. So it will reset back to his initial. Then we have also modulate 12 counter with preset. So initial, that is 0. When we have the first clock, we have 1. Second clock, we have 2. Third, fourth, then 8, 9, 10, 11, then 12. On the 13th, it will go back to your 1. So on the 13th, so this is equals to 1. This is 1. This is 0. And this is 1. So we have a 1 in your AND gate. And it is connected to your D in the set. So it means we have 1 here inside in your D flip-flop. This will be resetted to 0. This also resetted to 0. And this is also resetted to 0. So in the 13th pulse, so this is now our 13th pulse, it will go back to 1, not to 0. So if you have to count the number of pulses, that is equivalent to 2. So this is the same as modulo 12 because modulo means the number of pulses that your counter can count after before it will reset to its original value. So it is equivalent to 13. It will go back to 1. So number of state or pulses occur is 12. So for a binary, ripple counter can be used in the designing of your digital clock using the modulo counter. So for this 12, 59, 59, so we have a modulo 12 with preset, for 5 modulo 6, for 9 modulo 10, another 5 modulo 6, and modulo 10 for the last 9. So all these counter must be supplied by a clock pulse from your 555 timer. For the synchronous counter, it is a different from your ripple counter because it has a clock in all of the inputs of your flip-flops. A common clock triggers our flip-flops simultaneously rather than one at a time in succession as what you have in our ripple counter. So your synchronous binary counter is the same as what we have in our previous topic in the sequential circuits, in the analysis and design, and also in the before the FSM. So because if we see determine sequence in our example previous, when x equivalent to 0, your sequence is from 0 to 7 back to 0. So that is a determined sequence, increasing by 1 every clock pulse occur. So that is what you call your binary counter. So we have that example. This time it is a 4-bit counter, and it is binary counter because it incremented 1 data per pulse, or 1 binary data per pulse. So we have this excitation table. If we have from 0 to 1, 1 to 2, 2 to 3, 3 to 4, then we have 12 to 13, 13 to 14, 14 to 15, and 15 to 1. So getting the equation of your GE as well as your KA. Then for your B flip-flops or BFF, so we have your GB as well as your KB. Then for your DC, So that is our key C. And for your D, so we have GD equals to 1 and key D is also equals to 1. So we have to do the circuit. This is the circuit of your synchronous binary counter. Then we have also synchronous ring counters. It is also known as serial in, serial out shift register counter, where the output of your last flip-flop connected to the input of the first, which acts as a ring. So the mode of the counter is the number of unique states. So mode of n flip-flop ring counter is n. It can be implemented using D latches or cheeky flip-flop. So ring counters are classified into two. We have the straight type and the twisted type. So for your straight type, also known as the ring counter, another name for this one is also one hot counter, where the output of the ending flip-flop is given as a feedback to the input of the starting flip-flop, where binary digit is either 0 or 1 is circulated in a ring form. There are two control signals, the preset or PR and the clock signal clock are being used in this counter. So it is commonly known as the real ring counter. So this is the circuit of the ring counter. So we have your D latches, your D in your leftmost part of your counter. The input of this one is connected to the output of your last D, which is in your rightmost side. Then your PR is connected to your preset or to the tree, where the first flip-flop or D, the S is connected to your PR. So if this is our counter table, we have preset, the clock, your latches A, B, C, and D. So if preset is equivalent to 1, your A is 1, B is 0, C is 0, and D is 0 because it will clear all your B, C, and D, but you set 1 to your A. If preset is 0 and clear is 0, there is no change. If preset is 0 and clock is 0, there is no change in your counter. Then if clock equals to 1, your A will go to B, B to C, C to D, and D back to A. Then if the clock is in your second clock pulse, so we have your A to B, B to C, C to D, then D to A. Then third clock pulse, your A to B, B to C, C to D, then D to A. And in the fourth clock pulse, your A to B, B to C, C to D, D to A. So this time, it will rotate your value with is 1 back to his original latch, which is your latch A. For the twisted type, it is an alternative. Name of the twisted type is walking or Johnson type counter. So the complemented output of the ending flip-flop is feedback to the input of the starting flip-flop. So we have it's either 1 or 0 in your ring form. So this time also they are using two control signals, the preset with is PR and the clock. So for the twisted type, this is your circuit. As you can observe that your D in your leftmost, the input is connected from the rightmost output of Q bar. Then your preset for your are for your ring counter are connected to all of your R. Unlike in your straight type, when your preset is connected to the 3R, the other one is connected to your S. So this twisted type, all your preset is connected to your R input of your D latches. So we have your latch A, B, C, and D. We have your control, the VR or preset, and the clock. So when preset equals to 1, so all your data inside of your latches are resetted back to 0. So when clock equals to 0, no changes in your latches. But if your clock equals to 1, at the time PR is 0, the value of your D, which is 0 before, that is 0, but your output Q bar is the input of your A. So if your D is 0, Q bar is equals to 1. And with this 1 will be your data going to your A. So therefore, A has a value of 1, B is 0, C is 0, and D is 0. Then your second clock pulse. So your D has a value of 0 since your input at your A is connected to the complemented output of your D. So therefore, your A has a value of 1 again. The previous value of A will go to B, B to C, then C to D. A third clock pulse, then the previous value of D is 0, but since it is connected to your Q bar, then your value going to your A is 1. So therefore, we have now 1, 1, 1, 0. At fourth clock pulse, they are all 1 in your A, B, C, and D. In the fifth clock pulse, since your D that time is equivalent to 1, but your input to your A is connected at your Q bar, so the value that will go to your A is now 0. For 6, that is another 0 will go to your A. 7, another 0 will go to your A. So the difference between your straight type and twisted type counters, for your straight type or ring counter, the output of the last flip-flop is given as the input of the starting flip-flop. The number of states is equivalent to the number of flip-flops used. So if we have 4 states, so it means we have also 4 flip-flops being used. Then the input frequency is in terms of hertz or frequency. Then the output frequency, that is your frequency all over the number of flip-flops. Then the total unused states, that is 2 to the n minus n. Then for the twisted type, the complemented output of the last flip-flop is given as input to starting flip-flop. The number of states is equivalent to twice the number of flip-flops used. Then the input frequency is F, but the output frequency that is equivalent since we have twice the number of flip-flops of your number of states, so we have f over 2 to the n. And the total unused states, that is 2 to the n minus 2n. So what are the application of your ring counters? It is used as a frequency counter, analog to digital converter, and digital clock. So we have some problems. The first problem is we have a 6-bit counter in the initial value of 11010. 397 input pulses increment the counter. Then what is the new counter state? So we have to let IC as your initial count, in-pin number of pulses occurred, and number of state in a cycle, or that is what you call the modulus. Then C, number of cycle. FC is the final count. Then we have MC, the maximum count of the counter. So we have your solution. Our initial state is 111010, or that is 58. Number of pulses is 397. Number of flip-flops, or N. Number of bits, that is equivalent to 6. Then maximum count, that is 2 to the n minus 1, that is 63. Number of states is equal to 64. If we have to get the cycle, that is equivalent to the number of input pulses over the number of states. So we have 397 over 64. So we have only to get the next whole number value. So that is 7. So we have FC is equals to IC plus NP minus the number of state times your cycle. So we have 58 plus 397 minus 64, number of state. Then times 7, that is the number of cycle. So FC is equals to 7 since it is a 6-bit counter. So therefore we have 0, 0, 0, 1, 1, 1. Another example, if we have a 7-bit counter with 0, 1, 1, 1, 0, 1, 0 as initial count, then we have 9341 input pulses decrement the counter. So we have your initial 0, 1, 1, 1, 0, 1, 0, that is 58. Number of pulses 9341. Then number of bits is 7. So we have to get the maximum count of your counter. That is 2 to the n minus 1, it is 127, and number of states is 128. So number of cycles, that is number of pulses over number of states. Then we have 73 cycle for 9341 pulses. So we have to use this formula since this is decrement, so we have to subtract the number of pulses. And we have to add the product of your state times your cycle. So we have FC equals to 61, or in binary, since it is a 7-bit counter, we have 7 bits also to convert that 61. So you have 0, 1, 1, 1, 1, 0, 1 base 2. Another example, an 8-bit counter is in 1, 1, 1, 0, 1, 0, 1, 1 count. So there are 3973 input pulses increment the counter, and another 2188 input pulses decrement the counter. What is the new counter value? So first, we have to solve for the increment. So if it is increment, that is counting up. Initial 11101011, that is 235. During increment, we have 3973 input pulses. Since it is 8-bit counter, so n is 8. And the maximum count of an 8-bit counter, that is 2 to the n minus 1, that is 255. Then the number of states of your 8-bit counter is 256. Then we have to get the cycle. Number of input pulses over states. So we have 16 cycle. Solving for the final count after 3973 input pulses incremented the counter. So we have FC equals to IC plus NP minus your state times cycle. So we have 235 plus 3973 minus 256 times 16. So therefore, your FC is 112, or that is equal to 0.11100 base 2. And this value is your initial count for your down counting. For the 2188 input pulses decrement the counter. So initial, which is 112, or that is the final count after your counter incremented by 3973. The number of pulses that will decrement your counter is 2188. Then we have to get your cycle, that is number of pulses over number of states. So we have 9. So we have this one, FC equals to IC minus your number of pulses, because that is that will decrement the counter, then plus the number of states times the cycle. So we have 228, or it is equivalent to 11100,100 base 2. Another example, if we have a 5-digit modulo 10 counter with initial count of 77,876, and there are 99,793 input pulses, increment the counter. What is the new counter value? Initial count is 77876. Number of pulses is 99,793. The number of bits, or N, that is equivalent to 5, because it is a modulo 10 counter, so 1 modulo equivalent to 1 digit. So it is 5-digit modulo, so we have N equals to 5. The maximum count, that is 10 to the 5 minus 1, that is 99,999. Number of state is 100,000. So we have FC equals to IC plus NP, because it is to increment the counter, minus your number of states. So we have 77876 plus 99793 minus your number of states, which is 100,000. So therefore, FC is equivalent to 77669. So that is our new counter value. And that's all for our sequential circuits, register, and counters.